Thank you. Okay, so I guess, we are all sort of spending our lives trying to get some kind of model of space-time. And I'm going to sort of explain my own model of space-time, which is worse what it is, okay. And I am a mathematician, I'm not a physicist. And essentially, I try to use information from physics as very sophisticated computations that physicists do that are tested by experiment, and that somehow, if one looks at them carefully enough from the mathematical point of view, reveal amazingly beautiful structure. And I want to explain for two of these things. So the first one is renormalization. Okay. And the second one is the Lagrangian, which is the Einstein-Lagrangian plus the standard model Lagrangian. Okay, so I take this as being the basis. Okay, as being what is given by physics. So this is the pure gauge. This is the coupling of the gauge field with the X field. This is the quartic term for the X. This is a coupling of the gauge field with the fermions, and this is a Yukawa coupling. Okay, and the other one is the Einstein-Lagrange. Okay, so the idea is the following. The idea is that somehow I don't want to disturb these things. I take them for granted, given from physics, and I look at them as a mathematician. Not that I want to make it rigorous, I couldn't care the less. I just want to understand the meaning. Okay? So, as Mathilde explained, I will give a very quick summary of the work on renormalization. So, the work on renormalization can be summarized like this. First, in the work with Dirk Kramer, we understood that above the group of diffeomorphisms, or formal diffeomorphisms of coupling constants, of complexified coupling constants of the theory, there was a group which was lying above it that was mapping to it by homomorphism. And this group is the group G, whose Lie algebra, so if you want the Lie algebra of this group, is the Lie algebra which has a basis which is given by one particularly reducible Feynman graphs. And these graphs combine by insertion of one graph in the other, minus the insertion of the first graph in the second. This is a Lie bracket, which turned out to satisfy the Jacobi identity, which is not trivial. And when you are given the bare theory, when you work in the scheme which is dim-reg plus minimal subtraction, what you find out is that because of dim-reg, what the data, the physical data, gives you is a loop with values in G. There is a parameter in this loop, and this parameter is how far off you are from the critical dimension. So the number Z, which appears here, stands as, the excess of dimension, how far off you are from the critical dimension. So there is a critical dimension like D, okay, or let's say 4, and you are off by Z. So you have 4 plus Z, or 4 minus Z, this is the usual notation. Okay. Now, so you have a loop depending on Z, so it's really a loop. And it turns out that in geometry there is a well-known operation that you can do when you have a loop with values in a group. You can form a bundle which is obtained by using the loop as a clutching data. Now, deciding whether or not the bundle is trivial is deciding whether or not you have the Birkhoff decomposition, which is writing the loop as a ratio of something which is holomorphic in, well, let's say, in the upper hemisphere, which contains infinity, and the loop which is holomorphic downstairs. Now, what we proved with Dirk Kramer is that if you take the bare theory, so you don't know anything about renormalization, and you take the corresponding loop, if you want to obtain the value which is provided by dim-reg plus minimal subtraction, the only operation you need to do is the Birkhoff decomposition. Namely, transform this loop, just write this loop as a ratio, gamma minus of Z times gamma plus of Z. Now, gamma plus is regular at Z equals 0, so the evaluation is just you assign gamma plus of 0. Okay, so that's the summary of our work with Dirk Kramer. And in doing this work, of course, we were very struck by the fact that there was a Birkhoff decomposition, so it should be related to the Hilbert 21st problem of the Riemann-Hilbert correspondence, but we didn't have it. And we found it in the work with Mathilde Marcoli. So if you want, what we found is that, in fact, there is a group which is sitting above the group G, Okay, and it comes from the fine analysis of the mu dependence of the counter terms. This group, it's a universal group. It's a group which is rather sophisticated in the sense that, it's rather sophisticated in the sense that it has Lie algebra, which is quite fancy. Okay, and so it's a motivic Galois group. We found it by, I will explain it very briefly, by classifying the which gamma minus are obtained, and by interpreting them from a point of view of differential systems. But what was quite surprising, if you want, is that this group had been conjectured before. So it's a universal group. This group maps to the group of any given theory, and it maps exactly by the amount which is required in order to put the counter terms in the theory. So that's what it does. There is in this group a universal loop which will account for all the loops gamma minus, whatever the theory is. Okay? Now, what happens is that this group is really the renormalization group of physicists. So it contains a one-parameter group, but it's much, much, much more fancy. I remember once I was talking to physicists for a long time ago, and they were telling me the renormalization group, and then I was asking them what group it is. They told me it's a one-parameter group. I said, forget it, okay? But in fact, there is this extremely fancy group, which is a Galois group, and which has the following property. Cartier conjectured it slightly off. What Cartier had conjectured was that it was a group with free. It conjectured it from the number theoretic properties of the residues when you compute the Feynman graphs, because the residues are known to give you multiple zeta values and so on. And it turns out that this group is not the one that Cartier had conjectured. He had a free Lie algebra with one generator in each odd degree, and the group that we found with Mathilde, we found it by computation. Okay, so it's the Lie algebra of the group is a free Lie algebra which has one generator in degree 1, degree 2, degree 3, and so on and so forth. So the Hopf algebra of the group is what is called the shuffle Hopf algebra. It's algebra of shuffle relations. Okay, and it turns out, but this we don't have any explanation for that this group is also known in a completely different context, which is the context of the theory of schemes and motivic Galois theory, and that it happens, if you want, as what is called the motivic Galois group, which is the symmetry group of the simplest possible object besides spec Z. So it's not the spec of the integers, but it is the spec of the ring where you adjoin to the integers the root of -1, and you invert 2. And I have the sort of secret belief that this has to do with k-homology where you invert 2. But okay, I might come back to that later. Okay. So what we have, if you want, we have the following situation. That how does this group appear? It appears because we have a two-dimensional space, a geometric space, which enters very naturally, which is a space where the base is a complex dimension and you are off dimension by Z, and the fiber is a scale. So if you want, there is a sort of completely canonical space, which we are very well used to play with, where you have a scale on the one hand, and you have how far off you are from the critical dimension. Okay? And it's on that space that everything becomes singular when you are on the singular fiber over 0. And by studying the properties of what you obtain from quantum field theory when you go to the singular fiber, we fell on this group. Okay? This group classifies, this group gives you the Riemann-Hilbert correspondence between the type of connections, flat connections that you get from quantum field theory and representations of this group. There is this sort of natural correspondence. Okay. Yes, sure. Yeah, of course, yes, sure.
You all know very well
yes.
what the renormalization is.
Yes.
The object in the end.
Right. Yes. Right, sure.
What is this?
Okay. What is this bigger group telling you? Well, essentially what is going on is that this bigger group is going to act on the coupling constants of any physical theory, renormalizable, okay? And the way it acts essentially is, if you want, it acts almost by taking the powers of h bar. Which power of h bar enters? Yes. Usual renormalization group, yes. To the grading by powers of h bar. Yes. 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 Not really. It's not really. You mean of the map from G to diff? Oh, it's enormous, this kernel. Of this map here? No. Of U to diff? Well, this depends on the theory, of course. It depends on the theory. Okay, well, let me explain. You see, if you take a theory, the action on diff is given exactly by the divergences. Okay, so if you want, I consider the divergences as a blessing because they give you this action. If they were not around, the action would be trivial. So the idea is the following. The idea is that what this incorporates, it incorporates a kind of universal symmetry group, which normally one writes as simply a one-parameter group. Now it turns out that this group contains a canonical one-parameter group. And when you look at the composition, you get the renormalization group. But it is richer.
So if it's richer, you should learn something.
Yeah. Well, okay. I mean, fine. One has to look at a specific theory and look at what happens. But basically, what I was saying. Yeah. Well, basically, if you look at diff only, okay, you have the beta function. But the idea is that this beta function has components in every power of h bar, and that's more or less what is going on. Okay.
Isn't what you learned something about
Yes.
number theoretic properties?
Yeah, of course.
that hasn't been
Sure, of course. If you want, okay, it's the origin. Sure. No, of course. You see, the point is that, let me explain. I mean, this map here is complete. Okay, it uses full theory. The map which goes from here to here essentially only uses the residues of the Feynman graphs. Okay? In other words, you might have a graph which has, I don't know, 1,000 subdivergences, but you only care about the order 1 pole in Z. It is the only thing which matters. And it is these things which have number theoretical properties.
Right.
Okay? Which have number theoretical properties. In other words, it is these values which are not arbitrary numbers, but they are Police zeta values. They are, as you know, when you compute the anomalous moment of the electron, you have to use a value of zeta of 3. Okay, so this is typical of what you get here. Okay? You get number theoretical, what?
So is this a Galois group?
It is a Galois group,
The Galois group
essentially, of these values. Yeah, you can view it like this. You can view it like this. Yeah, you can view it like
seems like
this.
a very concrete way of thinking.
Yeah, it's a way to think about it. Yeah.
Okay.
Well, well, Greg, let's do it later. I don't want to be, okay. I want to go on, okay.
Well, wait a minute.
Yes.
Yeah,
Okay,
both
fine.
of you fine.
Okay, fine. Give me time, it's okay.
Consider the integral theory with those graphs and dimensional regularization. We have now dimensionally regularized integrals are the last series of groups. The residue of the ball is some number. Now, it's some complex number.
Yeah.
And now I think you want to say that you look at the complex numbers that you get for all possible
Yes,
time graphs.
right.
They generate a field.
Well, okay, no, that's too precise, but I mean...
And then you want the Galois.
well, yeah, I mean, morally it's what you have, okay? I mean, you would have to take very specific theory. No, it is, because if you want, what happens is the following. What happens is that in any given theory, you will have a realization, what is called a realization of this motivic Galois group, and, I mean, one has to compute it in every given case, but it will give, indeed, these values as periods for the corresponding realization, okay? Which is a very concrete number theoretical state, okay? I mean, this has to be done case by case. This is a completely general statement. What?
Periods are the residues.
Yeah, the periods are the residues, okay? That's a general statement, okay? What?
Did you do, for example, that,
Yes.
I mean, in low orders of perturbation theory, some classes of
Yes.
inner graphs,
Yes.
we know that these numbers often turn out to be,
Yeah, sure.
but I don't think there's,
No.
physicists don't know that
No.
the nature of
No, but neither do we. But if you want, it's not the point. I mean, the point is that, okay, what you have here, you have the general, completely universal symmetry group of the system. And in any situation, it will map to the corresponding group, but it will have to be computed in any given situation. So, I mean, you cannot say something general until you give me a completely specific theory. Yes.
So I guess I'm just trying to understand this.
Yes.
You're saying that if I know the theory and I compute all these numbers,
Yes.
then I know what the group is.
No, so good. No, not at all. By no means. No. What I am telling you, no, let me put it this way, okay?
It's really a Galois group.
Sure.
Start
No, but...
computing the values of the
Yeah.
zeta of 3. Take the zeta of 3. Okay?
Yes.
Now you have this group, this Galois group.
Yes.
Let me oversimplify.
Yeah,
it,
okay.
Then you apply that Galois group to zeta of 3. I don't know, you get zeta of 5, zeta of 5
Yeah.
squared of pi. I don't know.
Yeah.
So you get a bunch of numbers, and I think you're saying, roughly speaking, that those are going to be occurring
Yeah, but let me...
as a residue
Sure.
of the whole.
Yeah.
Arbitrary graphs. you could look at the set,
Yes.
the orbit
Right.
of the Galois group.
Yes. Yeah. Right. Okay.
It's going to give you a bunch of transcendental numbers, and
Yes.
those are the numbers that are going to
Yeah.
appear
Yeah.
as the residue.
Okay, but let me put it differently. Okay, let me say it differently. Okay,
Arbitrary.
let me say it differently. Okay, Mathilde explained very carefully. You know that we have what we are doing. We are dealing with vector bundles. Okay, which have a connection, and this connection is singular at the origin. All right. Now, what are these vector bundles concretely? These vector bundles are when you do computation, you do them to some loop order, some power of h bar, and they are filtered naturally. Okay. And you get a bunch of these things that Mathilde was describing. Okay. Now this group, universal group, tells you that whenever you have such an object, you have a representation of this group. Okay. That's what it is really. So if you want to think abstractly, that's really what it is. It's organizing all these computations once and for all by this Riemann-Hilbert correspondence. Okay. And these computations are all done over this group. That's all.
If you calculate, say,
Yes. Some order. Yes.
order,
Right. Yeah. Sure.
does it teach you anything about high order?
Well, it teaches you that it will be a final representation of this group. That's all. You know. I mean, what it does, you know, you can ask me. I mean, what it does to know that monodromy corresponds to differential equations. You can say it does nothing. That's not true, because what we have here, we have at every order we shall have a differential system, okay, which we are studying and which is over this base. The base is the complex parameter z and the scale, all right. And what this group is doing, it's organizing these computations once and for all by telling you that what you get are representations of this group. That's it. Okay? That's it. That's the correct standpoint. All right? Now, you see, let me explain from a mathematical point of view what this does. No, let me explain what it does for a mathematician. Okay? For a mathematician, it's fine. You look at books of physics and so on, and there are beautiful books, and they treat the master equation and all that. And whenever you read them, you find beautiful mathematics, up to a point where somebody tells you, but now you have to renormalize. So then you shut the book. Okay? But now, I am telling you what you can say. Now what you can say is that you forget completely about renormalization. You work with a gamma of z. Okay? And at the end of the day, you say, at the end of the day, I do the Birkhoff decomposition. And this is a beautiful mathematical operation, which is well defined and all that, and which has conceptual meaning. Okay? So if you want, that is telling a lot, because it's telling that you don't have to worry about this very complicated BPHZ rule and so on and so forth. No, now they are completely subsumed by a pure mathematical, completely conceptual idea, okay, which is behind the scene.
But in the end, actually do it.
Yeah, no, well, when you do it, you do the same. It's fine. It's fine, but you see, I am, yeah, sure. But you see, of course, and an example, let me give you a typical example. Here we are doing perturbative renormalization. Perturbative renormalization means that we are looking at the Taylor expansion, formal. Okay? Imagine that for some reason now in dimension z, I can go from perturbative to non-perturbative in dimension z. Then I will erect this Birkhoff decomposition to a principle. Namely, I will say, well, if the Birkhoff decomposition holds at the Taylor expansion level, why shouldn't it hold at the non-perturbative level? Okay? So this is typical.
Z is 1, does that mean you are defining a 5-dimensional monotonic?
Yeah, well, it would mean, yeah, sure, it would mean that you are working now in dimension z. Okay, well, wait a second, okay, fine. We are not yet there, okay? So, but what I'm saying is that, you know, there is always an advantage in stating a complicated recipe like BPHZ, which you understand perfectly from the physics side. I'm not talking about that. But encapsulating into a very simple mathematical law. Okay, this is bad. Now, it turns out, no, but you see, this was the work with Dirk. Now, the work with Mathilde was the following. Then, after the work with Dirk, Cartier had written this paper for 40 years of the HES in 2000, and I was laughing when I saw the paper. I said, what does this group anything to do with renormalization, this freely algebra and all that? Until we sat down and compute the differential systems and what was the corresponding motivic Galois group, and we found the same group. So, you know, it is also saying something, okay? And moreover, you know, now there are very fine works by Bloch and Dirk Kreimer and all that, who are in explicit example, constructing this motif and constructing the periods and all that. It's work which is not finished by any means, but it is indicating a certain direction, okay? And it allows for a mathematician, if you want to think about, to completely forget about renormalization and just think that it is this Birkhoff decomposition. For us, it's great, okay? So let's go on.
I have a technical question.
Right.
Does this apply also to gauge theory?
Yeah, it applies. This applies to gauge theory.
Only because that is if she
Yeah.
herself
Well, no, I mean, no, it's exactly what I was saying about the master's equation. So, you know, if somebody wants to do a thesis, you take the book by Saint-Justin, and in this book, when you find, for instance, you know, the place where there is all this mess, where you have randomization, okay, now what is needed is to put this Birkhoff decomposition together with the ghosts, okay? So the Hopf algebra might now be a Z2 graded Hopf algebra, where the ghosts have a strange behavior because they don't have the spin statistics correspondence, okay? And you want to put BRS, which is also something purely cohomological, and you want to blend them together. I don't think it is hard, okay? I'm not saying it is hard, but it doesn't be. No.
Is it going to be another group?
No. I mean, the only point will be that the group will be richer because it will incorporate the gauge transformations. That's all, okay? Sure, exactly, you know. Exactly, you know, I mean, exactly. You see, no, wait, okay? Yes, sure. No. Well, there is some nice work to be done to blend things together, but it will be it will be the group of graphs. But what you will do, you will incorporate BRS to simplify by what you should simplify by. Okay. Yeah, sure, the universal group will remain the same. You see, this universal group, I mean, you might say, okay, but you might have different beta functions when you have different couplings. This is completely taken care of, because the map to diffeomorphisms might be a higher dimensional diffeomorphisms. Okay, so let me now write the universal singular frame. So, you know, because this group is universal, it turns out that there is a counter term construction which is now universal. And we computed the expression for this universal gamma minus, okay? So it's given by a time-ordered integral, and we computed it, okay, in terms of the generators, and Z is the dimension, is the, by which off you, by how far off you are. Right, exactly. V is the scale. V is the scale, yes, exactly. Okay, so you have this formula, and then when we looked at this formula, we were very struck, because if you want, this formula is identical to a very close to a formula which is essentially non-commutative geometry, and which is the local index formula. So I will explain what is non-commutative geometry very briefly, but if you want the local index formula, what is it? It's a formula that generalizes the Atiyah-Singer index formula, but which fits exactly with the general framework of non-commutative geometry. And it was, I don't put it yet because it's a bit complicated, but if you want, it was very striking because it said that there was something going on. In other words, that this universal frame that was valid, you know, for normalization had something to say about this way of generalizing geometry.
I forgot what the E's were.
The E's are the generators of the Freely algebra. Okay?
So
this is in the enveloping algebra, right? Of the loop. It's a loop. Right. Yeah, I mean, in the group. It's an element in the group. You see, but you view it in the enveloping algebra. Okay? No. The Lie algebra is very far from commutative, of course, because it's a free. So free Lie algebra means there is no relation. Okay. Okay. So now you see we are looking for a geometry. We are looking for a geometry because what we would like is to go much further and get a geometric interpretation of this renormalization as being actually corrections to the geometry of space-time. That's what we'd like to think of. You see. In other words, I mean, okay, this is a dream, you know, I'm not saying we reached it yet, but the idea is the following. The idea is that, after all, what is going on, you know, of course, renormalization tells us that our idea about space-time is extremely naive, because the continuum gets screwed up by, you know, the self-energy of the field and all that. And what we know is that indeed, when we go to critical dimension, something strange happens. Okay. Now, you see, if you want to go anywhere, you need an extension of the ordinary G mu. Yes? Sure. Yes.
Those E's,
right.
My recollection
yes.
Is that
yes.
in this map here,
right.
U to depth,
yes.
the EN,
yes.
the
right there, right.
became something like
the nth component of the beta function.
Of the beta function.
Right, yeah, right. Yeah. Sure. In any coupling constant. So the beta function has several realizations for each coupling constant.
And now you've chosen a specific scheme.
Sure. Exactly. Okay, very good. Okay, so you see, now we are looking for a new paradigm of geometry. Okay? And we are looking for a new paradigm of geometry, and we want it to be flexible enough First of all, we want it to be a strict generalization of the Riemannian paradigm of the G minus. Okay? I mean, if it were something which would not contain the ordinary Riemannian geometry, we would not be happy. Okay, of course, because we know Riemannian geometry is immensely successful. Okay, so we want it to strictly contain the paradigm of Riemannian geometry. We want it to allow for complex dimensions. Okay, we don't want it to be stuck with integral dimensions, because that's no good. And we want it to be such that it still allows us to formulate what is quantum field theory over the given space. Okay? Well, classical field theory first, sure. Okay? I mean, if you want, okay, I can write classical. I mean, but you know, that's what you want. That's a basic requirement that you want. Okay, and what is it? I mean, what is this paradigm? I mean, this paradigm was obtained not at all from this motivation. It was obtained from a totally orthogonal motivation. And where did it came from? What is it? I mean, it can be said in an extremely simple manner. It can be said as follows. Let me explain it, you know. Let me explain, maybe I should even explain it on Blackboard. Okay? You see, I want you to retain one thing from this talk, perhaps it's this, okay? You see, we have a unit of, when we talk about geometry, in the word geometry there is meter. And the meter was defined at some point by people who were trying to be as clever as possible. So instead of defining the meter, you know, as the length of the pendulum which beats a second, something like that, they thought about a better definition. What did they say? They didn't have the Riemannian geometry, but it was all the same. They said, let's take a perfect circle on the Earth, which is the circle where the sun sets at a given time, which is called the meridian, and let's measure a certain angle in the meridian. So they measured something between, I think, Dunkirk and Barcelona. Okay, they went on, and they defined the meter to be a certain proportion to that, 1 over 40 million. Okay, then they say this is our ds, our unit of length. Now it's clear that if you carry it along in some other place, you can expand it in Taylor coordinates and you'll get your G minus. Okay, so that's a Riemannian definition. Okay. Now after a while, people found out that it was not very convenient when you want to measure your bed to have to go to Paris compared to the meter, you know, which is deposited in Paris and so on. So they really strived to find a better definition, and they found the meter that was in Paris was actually shrinking. So there was a problem. Okay. But they are physicists, they are very clever people, so they came out with a definition. And what is definition? The new standard of length turned out to be given in, I think, 67 or something like that, to be a certain wavelength of the krypton. And then it was replaced dually by a certain frequency of the cesium. But, you know, this is all the same. I mean, we all know that the speed of light enters and you can take the inverse. Okay? So if you want what physicists have done, they have changed the paradigm for the unit of length. And let me say one thing. You see, why is it so much better? It's so much better for one reason, which is that now you can make a unification of the metric system in the galaxy if you want. Because you can send out a probe where you will tell to people, take this chemical element, take that frequency, and this will be your unit of length. And they won't have to come to Paris. And the reason is that now your unit of length doesn't commute with the coordinates. It doesn't commute. If it would commute with the coordinates, it would have to be somewhere, because it's very small. It doesn't commute with the coordinates, and what is it? Well, what is unit of length? It's something that you all know. It is this little thing when you write Feynman graphs. When you write Feynman graphs, we have a propagator, which is a propagator for fermions. This is my unit of length, ds. So what does it mean at the mathematical level? At the mathematical level, it means the following. It means that we define a non-commutative geometry to be an irreducible representation, exactly as you define a particle to be an irreducible representation of the Poincare group. We shall define a geometry to be an irreducible representation. And it will be an irreducible representation in Hilbert space of what? Of the algebra of coordinates on your space. But that's not enough. It's not enough to do geometry. Having the coordinates is not enough to do the geometry. To do the geometry, you also need the line element. So we shall define a non-commutative geometry as being a representation in Hilbert space, this is the Hilbert space, of the algebra of coordinates, but you enrich it by the inverse of the line element. So this has the dimensions of frequency. Okay? Now let me explain that this strictly contains Riemannian geometry. How? I have to start by that. Okay? In that case, H is the Hilbert space of spinors, D is the Dirac operator, and A is the algebra of functions on the manifold. Now you can tell me, what if the manifold is not spin? Well, you replace functions by sections of the Clifford bundle, and that's it. Okay? So I mean, it's absolutely clear that it contains the ordinary Riemannian geometry strictly, okay, and we shall recover all of the ingredients of ordinary Riemannian geometry from this data, from this purely Hilbert space theoretic data. Wait a second, I'm not talking just about D, I'm talking also about the algebra. So the algebra is also given, okay? Okay? In the commutative case, it's just functions on the space, on the manifold, okay? Okay, fine. How does D give you the line element is the inverse of D, okay? But let me show you how to measure distances. Let me immediately show you how to measure distances. Yes?
The inverse of D is
Yes.
propagator.
Yeah, it's a propagator.
Green function for the Dirac operator.
Right. Yeah, okay.
How do you get the line element?
This I define to be the inverse of Dirac, okay?
Gamma squared
Right.
is -1.
Yes.
The Clifford multiplication. That defines
Yes.
the metric.
Exactly. Exactly.
You couldn't get the Clifford algebra without
Sorry, there's no dimension.
What?
There's no dimension of length.
Let me explain how you measure.
How you get rid of the unit length.
Oh, let me show you the formula to measure the geodesic distance in the Riemannian case, okay? So in the Riemannian case, I am saying that the ordinary geodesic distance can be measured now. Instead of pulling a cable between 2 points as tight as you can, you will do something totally different. You will take a supremum of a phase shift. You will send a wave from one point to the other with a limited energy, and you will take the maximal phase shift. So what is this formula? The distance between x and y is the supremum of the difference of the value of a function, and the line element doesn't commute with functions. So it has a commutator. You require that this commutator is bounded by 1. You see, D has dimension of a frequency, the inverse of a length. So the result here has dimension of a length, because it uses the inverse of D. Okay? Because it uses D times F equals something. Okay? So that has dimension of a length. And now exercise, which you can do on the back of an envelope, in the Riemannian case, this gives you on the nose the supremum over functions, over all F satisfying the condition that D commutator F is less than 1. Okay? This is saying if you want that the function has a finite oscillation energy. It cannot oscillate too fast, because otherwise the commutator would be big with the Dirac operator. Okay? So it's an exercise. It has to be fine. It's an exercise. Now the geodesic flow, what replaces the geodesic flow is the exponential of IT, not D, but absolute of D. Okay, this is what replaces the geodesic flow. And the analog of Newton's law, namely the geodesic equation, is given by this formula. Okay? Yes?
It's an exercise.
Let me tell you the reason.
Many of us very non-trivial to see how this and the community case.
Fine, let me do it. Okay, it's an exercise, let me do it. Okay. Now, let's compute the commutator of gamma mu d by dx mu, okay, with a function. What do you get? You get gamma mu times d mu of f. This is the image of the gradient of the function by the gamma map. Okay? The size of that is exactly the size of the gradient of the function. So saying that the commutator of the function with the Dirac operator is less than 1 is saying that the gradient of the function is everywhere less than 1. Integrating over a little path, this is saying that the function is ellipsic of constant 1. Namely that it satisfies... Yeah, sure. It's all Euclidean, it's all Riemannian, okay? Now, so this is telling you that f of x minus f of y in absolute value is less or equal than the distance between x and y. So the only thing, so you have the inequality one way. If you want to get the inequalities the other way, you just have to find a clever function that does that. What is that function? It is a distance from a point to the point x. Because it is, of course, Lipschitz of order 1, and when you evaluate it at the point y, it does the job. Okay? So that's it. All right, so you see what happens for the distances. But now the beauty is that this geometry doesn't distinguish between the discrete and the continuum. Because if I have a space which is not the continuum...
But in this definition,
yes, sure.
What is special about the Dirac operator? Couldn't I have used the square root of the Laplacian?
You could have used the square root of the Laplacian. We shall see that the fact that we have taken the Dirac operator is related to something which is far more fancy, but which is what is called the fact that we are dealing with a manifold, namely the k-homology fundamental class. If you want the sign of the Dirac operator, is giving you the Pontryagin class of the space. So if you want the space in question, when you think about a manifold, you can think about a manifold as obtained by gluing little patches together. This is a naive conception of a manifold. What is a non-naive conception of a manifold is that it is a homotopy type plus Pontryagin classes. Okay, and Pontryagin classes will be a byproduct of this Dirac operator. Okay,
But just for the metric,
just for the metric.
any differential operator.
Well, if you take a different differential operator, you'll get a different metric.
But
That's all.
still the possibility.
Yeah, but I mean, in general, you could take a Finsler metric, for instance. Okay, you could also obtain a Finsler metric. Okay. Now, fine. Okay, so what I'm saying is that the only thing I just said so far is that it does contain, if you want, the Riemannian case.
When
Yes.
you specify the
Yes.
unit of the length or line
Yes.
element,
Yes.
is that part of the algebra? How do you specify?
Okay, a very good point. You see, what happens, indeed, you're right to ask this question. What happens is the following. What happens is that you have your coordinates, all right? And now you want to think not only of your coordinates, but also of the line element. And you can ask me what are the relations between the coordinates and the line element, if any. Now, I ask you as an exercise, okay, to recover the geometry of the circle with its standard metric of length 2 pi and all that, just from the following extremely simple equation, which is that D commutator with U is equal to U. I claim this is a kind of Heisenberg commutation relation. You can look at the irreducible representations of this relation, and you will find that the spectrum of U gives you a circle, and that the metric defined by the operator D is the standard metric with length 2 pi. Okay? Now, in general, when you are dealing with a manifold of dimension n, the relations between the coordinates and the operator D is a polynomial equation of degree n. Okay? So I will eventually come back to that. Okay? Fine. Yes? Yes?
Does this still work in Lorentzian signature?
No, this is in Euclidean signature. When you work in Lorentzian signature, you have to be a bit more careful. But basically, instead of here, you require that the operator D is self-adjoint. This is what is characteristic of Euclidean signature. Okay? If you want to work in Lorentzian signature, you can require that the square of D is self-adjoint. That will incorporate the Dirac. No, the definition of distance, you would not, if you are in Lorentzian, you would not take a supremum. You take a local maximum or something like that. I mean, it's good only in the case to take a supremum, obviously. Okay. Well, I suppose there should be a way where you consider, according to situations where it's a supremum or a minimum and so on. You have to, of course, be careful. But, I mean, all of what I will explain is Euclidean. All right? Okay, so now if you want, I don't want to bore you too much with the general framework. Yes? Yes?
You also have the volume form.
Yeah, sure. Okay, so how do you obtain the volume form? Okay, it's an amazing thing, actually, that in the framework, so yes, I have to put a little bit of the framework of non-commutative geometry, that there is a completely general replacement for the integral and for the calculus in non-commutative geometry. So what is the calculus and what is the integral? It's completely general, you see, and it comes from quantum mechanics. Because after all, so you know about it. I mean, in quantum mechanics, you know very well that it's not a good idea to think of a variable as being a map from a set to the real line. There is a much, much better idea of variable, which is a self-adjoint operator. Because a self-adjoint operator, a variable has values, and these values are rich with some multiplicity. But the values are the spectrum of the operator, and the multiplicity is the spectral multiplicity, and so on and so forth. And and it's much more agreeable to work with operators than to work with variables. But the beauty is that in the operators, you have a room for infinitesimals. They're all there. There are operators which are very small. What does it mean, very small? It means that if you condition them by finely many linear conditions, their size will drop to nothing. These operators exist. They are called compact operators. And in particular, these operators have an order, which is very nice, because an operator which is compact, the characteristic values of the operator decay to 0, but they can decay like 1 over n, like 1 over n squared, and so on. And the integral wipes out all infinitesimals which are of order bigger than 1. So the integral in non-commutative geometry has a merit that it goes back to classical. It gives you a classical picture of the space. Okay, and this will be the residue, and this will be how we get the locality in general. So the notion of locality in non-commutative geometry is coming from the integral.
What is the trace of
Okay, you see, you have an operator. This operator could have eigenvalues like 1, 1 over 2, 1 over 3, 1 over 4, and so on. You order them by decreasing. Okay. Now, if you try to sum these eigenvalues, you get the harmonic series. It's divergent. So what you do, you cut it off at lambda. That's what I call the trace cut off at lambda. Okay? So for an infinitesimal of order 1, since the eigenvalues decay like 1 over n, it will diverge logarithmically. Okay? And then you have a coefficient of the log. Yeah, I take the coefficient of the log. Okay? So if you want, it was a remarkable result of Dixmier. Dixmier was looking for a counterexample actually, but he found that this defines a trace, which is quite amazing. You know, it's quite amazing.
Only operators that are harmonic, the eigenvalues look like harmonic too.
Well, they can be, if they go faster, it's okay. If they are summable, their integral is 0. You see? So,
If they go faster,
the integral is 0. So, which means that the integral of dx square is 0. But the integral of dx is interesting. Okay? So the integral of an infinitesimal of order 1 is interesting, not if it is order 2 because it's 0. But what we shall see is that now there is something completely amazing which happens, and this is what I had put before, which is that now, if you want, what happens is that you think you have done nothing because you have replaced the integral by this, which gives you the volume form. I mean, in the Riemann case, this integral, this new integral, which is the logarithmic divergence of a function times the line element to the right power. Okay, for instance, if I am dimension 4, this would be power 4. So if I take this integral, it will give me the volume form, the Riemannian volume, square root of g d4x. Okay? But now I can ask a completely crazy question, which you could not ask in the ordinary case. I can ask what is the area of a 4 manifold. Okay? And it has an answer. You compute the answer, and you find the Einstein-Hilbert action. Namely, you find that the area of a function times ds square, okay? You see, this obviously has dimension of a length square, okay? And this you find that it is equal to the integral of the scalar curvature multiplied by the function.
Anyone can deduce from the time expansion of the
Yeah, sure. Okay, but now let me introduce a fundamental notion. Okay, there is a fundamental notion which is hidden behind all of what I said, which will play a crucial role in the rest. Oh, I should not have erased this, but okay. So if you want, there is an absolutely fundamental notion, which is that in non-commutative geometry, dimension is not a number. Okay. Okay, so you see what happens is the following. What happens is that... Yeah, sure, yes.
Is F supposed to be 1?
No. Oh, you can take F to be 1 if you want, to get the Einstein-Hilbert action. But
A volume form for any F. Is that
no. If you what is a volume form? It's a linear form on functions. It's a current. It's a Durham current. Okay. Well, I mean it's to their integral. Sure. Okay. Okay. So, but now let me make the main point. The first very, very important point is that when you consider a non-commutative space, its dimension is not a number. Its dimension is a spectrum. Okay. So, in other words, what you do is, there is a certain formula to compute it, which is by zeta functions and all that. And what you find, for instance, you find that if you take a manifold of dimension 4, okay, you can sort of try to look at it with an X-ray spectrally and see where it exists, in which dimensions it makes sense. You will find that it makes sense in dimension 4, it makes sense in dimension 3, dimension 2, dimension 1, and dimension 0. Okay. The manifold. Okay. Now you can do that with a counter set. Okay. So you can do that with a counter set. You take counter set, and what you find is very strange then, because what you find is that the counter set exists, of course, at the Hausdorff dimension, which is to be expected. Okay. But it also exists in an harmonic sequence of points which are above the complex dimensions and which are spaced by the scaling ratio of the counter set. Okay. So if you want, what happens in general? Okay, how is it related to the Dirac operator? It's related to the Dirac operator by the following fact. Essentially, these points are the points where you will have a non-trivial residues to zeta functions. Okay? And zeta functions will be of the type some trace times some pseudo-differential operator times d to some power minus v. Okay? Okay.
So again, so that's where you. So these are the values.
These are the values of z for which you have a residue. Okay? Okay? And now it's a general theorem. Of course, you know, this was discovered first by Wojcicki in the case of pseudo-differential operators, but it's a completely general theorem in non-commutative geometry. that the residue gives you a trace, extremely interesting trace, which exists for all these values, okay, and which allows to test the space in all these values, okay. Now, so if you want, now I can put a formula for the local index formula. Yes. Yeah, no, I can tell you. No, I can tell you. No, I can tell you. No. You see, what do you have? You have the line element and the functions. Putting them together, you get the pseudo-differential operators. It's not difficult to understand. Okay, I mean okay. So what you do is you take a pseudo-differential operator and you look at this function. This function is a holomorphic function for p of degree 0. Okay. So it's a pseudo-differential operator of degree 0. Now that function will make sense when the real part of z is large enough. Okay, because this operator will be trace class. And now you ask for analytic continuation and you look at the singularities. And you look at the residues. And the residues give you exactly these dimensions.
Residues are the trace
right.
P
yes.
for that dimension.
For that dimension. Okay? And the amazing fact is that it's still a trace and it has the right properties and so on. Okay? And it can be computed locally. And the notion of locality in noncommutative geometry is that one. In other words, I have to explain that because, you know, I saw at some point there were many papers about locality, noncommutative geometry, and so on. Of course, the noncommutative space doesn't have points which are so easy to understand. So what does it mean to be local? We are always working in momentum space. Always. And local means really at infinity in momentum space. And what it means is because it's a residue of a quantity like this, it simplifies by a lot of stuff. So all the details of your operators, you know, all the fine details of the matrix and so on are totally irrelevant. And there are examples of computations like with quantum groups and so on in which one can see that, one can witness that extremely clearly, even though there is no space at all. So, I mean, locality means that you throw out the very high frequency details. Okay, that's what it means, really. All right? Details. Okay? That's exactly what it means. Okay. Now, what happens... What?
Alain, may I?
Our intuition would be on the contrary. It's only local when you
Yes.
have ultimately infinite frequencies.
No, but you don't see the point. No. By details, I mean things which are valid for low frequency. In other words, what is local is the asymptotic expansion at high frequency. This is what is local. You see, if there is something, what I am saying is that if there is something which was occurring for low frequencies, okay, I discard them. This is not important for the local behavior. The local behavior is only the asymptotic behavior at infinity in ultraviolet. Okay? I mean, well, okay. I mean, this is, you know, this we all know that. Yes.
This is out.
Yes.
They're so used to quantum mechanics
Yes.
and the path interval formula for the E curve.
Yes. Sure. Yes.
You take the trace E minus T times the Laplace.
Sure.
What does that look like for T small? It's 1 over 4 pi T to the dimension.
Sure.
So you use that to define dimension.
Yes. Sure. Exactly.
So
Sure.
also
It's a variation.
Yes.
This is reconstructed geometry like
From the Fourier space. Exactly. Exactly. Sure. You see, the right name of the geometry I'm talking about is spectral. The correct name of the geometry I'm talking about is spectral. And I just want to make a point, because, you know, this place is a place which is centered on gravity and so on. And I just want to make a point. I mean, the point is the following. The point is that when we are talking, and I hope I will come to that, but when we try to talk about gravity, we should first think about what are the observables in gravity. And the observables in gravity are certainly quantities which have to be invariant under diffeomorphisms. Okay? And it's not easy to fabricate something which is invariant under diffeomorphisms. It's not easy at all, because the distance between this point and that point is not invariant under diffeomorphism by any means. Okay? Now, the point of this theory that I am talking about is that it's a spectral theory. And the spectrum of the Dirac operator is, of course, an invariant under diffeomorphisms. Okay? And so we want to reconstruct, the idea is that we want to reconstruct a picture of space-time and a picture of the world from spectral data, purely from spectral data. That's all. Okay? So that's the idea. Now, okay, so now if you want, I can put in the local index formula, so I won't detail it, but it was quite striking at that point, if you want, that the coefficients in the local index formula were exactly the same as in the... He's coming back. He told me that he's going to give a phone call. He's coming back. So you see, the point is the following. The point is that this residue, which is a trace, okay, and which is local, which can be computed locally, it allows, in fact, to have Pontryagin classes in the generality of non-commutative geometry. So I don't want to insist on that. But the point is that one has a framework in which you have spaces, they have characteristic classes and all that. Okay? And all of what we know usually does work. Okay? Formulas are far more involved. And what was striking is that in this index formula, there were these strange rational numbers which were entering. And we had no clue for what they are. And then we were very pleased to see that they are the same as in this universal singular frame. Okay? In renormalization. Well, the gamma function is very little. I mean, it's okay. There is a gamma function, but you know, it's like. You can't just observe that as the normalization. No, but you do absorb this in the redefinition of the Bn case. I mean, the Bn case, you know, you have this term at the end with the power of d, and it should really go with the gamma. You see, the gamma which is here, it's the same as the one that comes from the power of d. Really. Okay. Okay. So now what happens is the following. What happens is the following. Okay. What happens is that you can keep going and do this geometry. Yes. No. I said nothing. I have said nothing. I have said there is a strange coincidence, okay, between the numerical factors that occur in the universal singular frame and the numerical factors that occur in the definition of the Pontryagin classes. Okay, that's all. Absolutely nothing else. No. Okay, no, not at all. Okay, so you see, you keep going, you define this geometry, you see that it has a certain number of remarkable qualities. Okay, I mean, as I said, you know, this. Okay, so I mean, you see many properties of this geometry. One of them is that it treats the continuum and the discrete on the equal footing. And the point is the following, is that when you are measuring distances, you are not pulling a cable between 2 points. So a space which is disconnected will still have a distance, because you can still send a wave from a point to the other with this bond. Okay, so it does this. I mean, another thing that it does is that it treats spaces of infinite dimension and, you know, non-commutative space and all that. And so it is something which is incredibly flexible. Okay. Now, what? So with Mathilde, we found something last spring. Sorry. For the moment, it's only Archimedean. I mean, it's only over the complex numbers. But okay, that's an interesting question in the sense that there are other domains, like the work we do on number theory, where non-commutative geometry now comes face to face with the theory of motifs for other reasons. And there, okay, I mean, it's not always Archimedean in the sense that it treats adelic space and all that. You know, I mean, these adelic spaces fall under this general framework as well. Now, what we found, which is very strange, is the following. As you know, dimensional regularization is very sort of tricky when you have gamma 5. Okay? And I never looked in the paper until we started with Mathilde to look at this situation. And what happens is the following. What happens is that, well, my source was a book by Collins. So, I mean, maybe David tells me that it's not the right reference, but okay. But I mean, there is certainly a prescription. Okay, there is a prescription which is due to Breiteln, Maison, and to Weltman. Okay, to handle the fact that you have gamma 5, and that it is not easy to deal with gamma 5 with dimensional regularization. Okay. Now, the one thing which I find extremely striking is the following: is that in non-commutative geometry there is a notion of a product of two spaces. What is it? Well, you have a space which is given by AHD. Okay, A1, H1, D1, and you have another space which is given by A2, H2, D2. Okay, and it is simplest to do it with when one of the spaces is even dimensional, so there is a gamma 5. Okay, so how do you get a new space? You get a new space which is a product of the two by taking the algebra which is A1 tensor A2, that's very simple. Taking the Hilbert space which is H1 tensor H2, that's also extremely simple. And taking the Dirac operator to be what? To be D1 tensor 1 plus gamma 5 tensor D2. And what is the interest of this gamma 5? You see, it anti-commutes with this D1. So it tells you that when you square, there will be no cross terms. But this is a general procedure in what is called cohomology. I mean, it's not something you invent, it's something that you take from the book. All right, so this is the product of two spaces.
And in the usual description, this corresponds.
Exactly.
Okay, so there you.
Yes. You see,
Gamma 5.
in a very strange way.
Gamma 1, gamma 2, gamma
Right,
3.
yeah, exactly. You see, there is this strange prescription, which I never liked at all, until I understood that, in fact, it is on the nose. Taking the non-commutative space that you start with, which is, say, four-dimensional space-time and so on, and tensoring it in the sense of non-commutative geometry by a very specific spectral triple, whose dimension spectrum is just the point Z. Okay? And what happens, I mean, I don't want to spend too much time on it, but I want to explain one absolutely key feature in general to be able to understand this point, but it's also an absolutely key feature in general. You see, and now you can ask me the following question: what are examples of phenomena which are purely non-commutative? Namely, what are examples of phenomena which have no analog in the commutative situation? Okay? So let me give you new features of non-commutative spaces. New features, absolutely new features. I mean, on Monday I'm going to tell you a feature which is incredible, which is that the non-commutative space can be cooled down and distilled. Okay? But for now, I'm going to give you a much milder feature, new feature, okay, which is infinitely milder and easy to understand. So what is this new feature? The new feature is the following, is that when you consider a commutative algebra, okay, you can think of it as a set of points and so on, and when you think of it about a space, the diffeomorphisms of a space X, that would be the same thing as the automorphisms of the algebra of functions on X. Why? Because if I have a function on X, I can reshuffle it by a diffeomorphism. Okay? So the diffeomorphisms are just the automorphisms of the algebra. Okay, so this is my algebra A. But now, you see, unfortunately, I have erased the Lagrangian that I had before. Remember that I had this Lagrangian, which was LE plus LG plus LGH plus LH plus etc. Now, this Lagrangian, when you look at it, you find out that its group of symmetries is a bit more complicated than just diffeomorphisms of space-time, because it has gauge transformations. Okay? Now, what yes?
You're not discussing particular concept.
No, not yet, okay? But
I understand that you have to find for us because
yes.
how to do it.
I'm going to come to that. I am coming to that, okay? I am now going to define the gauge bosons, okay? So it's in general. Yeah, well, I mean, in general for non-commutative spaces, okay? So what I am saying is the following, that when you consider this Lagrangian, for instance, you find out that its symmetry group, the naive symmetry group, is not only diffeomorphisms, but it's also gauge transformations. And the full group of symmetries is not the product of the two, because diffeomorphisms shuffle gauge transformations. Okay? So if I look at the group of symmetries of that, okay, so if I look at symmetries of this guy, what I find is that it's not diffeomorphisms, but it's diffeomorphisms semi-direct with gauge. All right? And now, for me, this is a big flow of Kaluza-Klein, because diffeomorphisms with gauge, I can ask, is that diffeomorphisms of another space? Okay, of some putative space Y. But this cannot be, because it's a theorem in topologies that diffeomorphisms of any manifold is a simple group. It's a simple group that does not admit a normal subgroup. Okay, so you're stuck. So in the commutative world, you're stuck. Okay? You cannot write this group. This group is a group which is not simple. It's like the Poincaré group. The Poincaré group has this normal subgroup of translations. It's not a simple group. So you are stuck. Now what happens? What about a non-commutative space? Well, a non-commutative space has trivial automorphisms. What are they? They are the inner automorphisms. So when you have a non-commutative algebra, you have a subgroup of the group of automorphisms, which are automorphisms of the algebra, which are of the form F goes to UF U star. Okay? I mean, you will admit, or UF U inverse, if you want. These are called inner automorphisms. Yes.
4 steps back, but I still wasn't fine.
Okay.
There's another.
I mean, there are other transformations in this Y besides. I mean, it doesn't diff X and the direct gauge the subgroup.
It's it as a subgroup, yes. Sure.
Subgroup,
Yeah.
Okay.
But you cannot say it's pure gravity because you have to require that you are in this subgroup. Okay?
Fair enough.
Yeah. Okay. So you are not with pure gravity. I mean, you are imposing something on the fibers. All right? Okay? Fine. That's what I mean. Okay. I'm looking for a theory that would be pure gravity. That's what I'm looking for. Okay? Now, what I am saying is the following: that if I consider a non-commutative space, so this is a new feature, which doesn't exist in the commutative case. Okay? What is a new feature? The new feature is that an algebra which is non-commutative has certain special automorphisms of a very trivial kind, which are just conjugating by an element of the algebra, UFU star, or UFU inverse, if you want. Of course, if the algebra is commutative, this is the identity, so there is nothing going on. Okay? But when the algebra is not commutative, it happens that it has these special automorphisms, and they are, because they are so special and natural, they form a normal subgroup. So that the group of automorphisms, I mean, you know, the group of diff will be a little bit more evolved than that, but I mean, naively, the group of diffeomorphism would just be that. And it's not a simple group, never, because it always has this normal subgroup of inner automorphisms, and the quotient group is called the outer automorphism group of the algebra. Okay? And you always have this exact sequence. Okay. Now, this is fine. It tells us something about the diffeomorphisms. What about the matrix? And it turns out that the situation is similar for the matrix.
I'm
Yes.
really confused. You said that this X is a simple group.
Yes.
And you said that in the commutative.
In the commutative case. Okay. Okay. But what I am telling you is that, I mean, whatever I will take as definition of diffeomorphisms of a non-commutative space, it will never be simple. Okay? And if we are clever enough, we shall identify the inner automorphisms or the internal automorphisms with the internal symmetries of physics. Okay? And the vocabulary is the same. So that's a good start. Okay. Fine. So that's the idea. That's the idea. The idea is that already for diffeomorphisms, you have something new, something very special that occurs in the non-commutative case. Okay. Now, what about the matrix? What about the matrix? If for diffeomorphisms we have these special ones, for the matrix we should have something similar. Okay. And this comes from the following. It comes from the treatment of Morita equivalence, which I have to explain. So this is again a phenomenon which has no counterpart at all in the commutative situation. What happens is the following. What happens is that when you have a non-commutative algebra, okay, A, well, you know, essentially what happens is that if you replace it by the algebra of n by n matrices over A, essentially nothing changes. Very little changes. I mean, all the invariants like K-theory, everything, you know. And so, I mean, this is what is called Morita equivalence, but I will only use the Morita equivalence of A with A itself. Okay, so I mean, this is not a big deal. Okay. Now, in more algebraic terms, you know, instead of taking matrices, you should say that you replace A by endomorphisms of a finite projective module, right module over A. This is just a fancy way of saying the same thing, because Mn of A, it is just the endomorphisms over A of the direct sum of n copies of A, which you view as a right module over A. Okay, I mean, this is, you know, it's just language. Okay, so there is this transformation which we call Morita equivalence, and we call B the algebra which is Morita equivalent. Okay, now there is an obvious question, which is how, if I have a metric for A, can I transfer it to a metric for B? You see, I mean, this operation would give you nothing in the commutative case, but in the non-commutative case, it's very natural to ask the following question: if I have a metric for A, can I get a metric for B? And how does it work? So what you have is a spectral triple for A. Okay, so on A, if you want, you have a representation in Hilbert space and you have a Dirac operator. How are you going to get one for B? Well, the Hilbert space is very easy to get. The Hilbert space is just the tensor product of epsilon over A by H. That is very easy. You know, this is extremely simple. Okay, but the operator is not easy. Why? Why is it not easy to take the operator? Because naively you would say that I am going to take D prime, the new metric, to be one tensored by the old metric D. Why doesn't it work? It doesn't work because it's a tensor product over the algebra. A. This is how the gauge bosons are going to appear. Okay, so this is very important. This is how the gauge bosons are going to appear. Okay, so what I am telling is the following. I have a metric on my algebra. I am trying to transfer it to a Morita equivalent algebra. Okay, and if I try in the most naive way by taking one tensor D, why doesn't it work? It doesn't work because this operator, to make sense, it should make sense on the tensor product of epsilon over A by the Hilbert space H. But there is a simplification over A, which is telling you that a vector psi A.
Tensor over A in the operator. But you're saying that the naive tensor product is not a.
It's not an operator here.
It's not even defined.
It's not defined. It's not defined here. Why? Because it should simplify with the equivalence relation, which is psi A tensor eta is equal to psi tensor A eta. In order to do that, you would have to commute A with D. But we know exactly that the coordinates don't want to commute with the line element, with the D. Okay? They don't. And in order to correct, you don't have a choice. You are forced to introduce gauge potentials. Namely, the only way to do it, okay, is to add to the naive definition a connection. What you have to do is to add to one tensor D something which is del times 1. And what is del? It is a connection, namely it's satisfying the Leibniz rule. Okay, so what is del? If you want, del is a map, linear map, from epsilon to epsilon tensor over A with omega 1. And what is omega 1? Omega 1 is exactly what you get by permuting D with A's. Right? Now you see, okay, I am sorry that this is a little bit of algebra, but it is completely forced upon you. And what I am telling is the following, is that from the fact...
Isn't this...
Yes?
Maybe I don't understand, but it sounds like
yes.
what you do in physics,
yeah.
you approach the necessity of division, so say,
yeah.
here's a representation of the matter,
yes.
that's this tensor
right.
right. Given that,
yes.
given the Noncommutative,
sure.
you
yeah.
You have to
sure, but let me tell it in a much better way. I mean, you see, what happens here, we are only talking about metrics. And what is the situation? Exactly as you have inner automorphisms, in non-commutative case, the matrix will be foliated. So the space of matrix will have a natural foliation, where to a given matrix there correspond a whole class of metrics which are almost the same. They are like inner conjugate. And they will differ from the given one by gauge potentials. Okay? And if you do things accurately, I mean, I don't have time to give you the details, but if you do things accurately in the commutative case, this gives you nothing. It only exists in non-commutative case. Okay? Exactly as in automorphisms only exists in non-commutative case. Okay, so what do you do? What I am saying is the following, is that by the necessity, by the Morita equivalence of the space with itself, which is a stupid thing. Okay? Now, your algebra is of course Morita equivalent to itself, because it's endomorphisms of A. So just by that, you are forced to replace the metric by the whole leaf of the metric. Okay? Namely all these gauge potentials. Okay? And now, okay, so as you say, I mean, in the physicist language, it's what you say. But the beauty now is the following, is that if I now come back to Dimreg and to this product space and so on, and I do this computation, I find exactly the evanescent gauge potentials of the Breton-Lohner. I find exactly what are called the new gauge potentials which you have to add in order to do Dimreg and anomalies, and what are called evanescent gauge potentials. So, okay, I mean, I don't want you to give details about this, but it is another very strong reason why this general procedure actually applies. Okay, so, I mean, in that case, you do a computation and you find exactly these evanescent gauge potentials, which are new gauge potentials which exist in the product space of dimension 4 plus z, but which vanish to 0 in the space of dimension 4, and which are absolutely instrumental in making traces finite. You see, normally you would have expressions that would be divergent, they become convergent because of this guy. Okay, so that's what you find. All right, so I mean, then okay, there is a small development. I mean, you know, okay, one can do. Yeah, exactly. I mean, so if you want, what one can do with this, we have not written the paper yet with Mathilde. I mean, what we are doing is we are writing a paper in which what we do is very far from doing quantum field theory in dimension 4 plus z yet, but there is something before which has to be done, which is to redo the computation of anomalies for any non-commutative space, and including then the standard model and so on. And it turns out that it is possible and that it relates to the local index formula with Henri. Okay. So, well, okay, of course, I mean, this is not very new in the sense that we all know since very long, that anomalies are related to the index theorem and all that. That's not the point. The point is to have it in this completely general framework. And, for instance, in the work with Henri, we were using what is called analytic regularization. Namely, raising the propagator to the power z. Now, which is not nice. But now we can prove that it is the same result as the result which is obtained by Dimrek, which is much nicer, infinitely nicer. Okay. So if you want now, in general, what is the general strategy? So the general strategy is that it is the fermions in this theory. The whole story is specified by the fermions. In other words, when we are talking about a space, a non-commutative space, the Hilbert space is the Hilbert space of fermions. And, okay, the chirality is a grading. As I say, the internal symmetries will turn out to be given by the inner automorphisms. And the gauge bosons of the theory will be given by the internal fluctuations. By internal fluctuation, I mean what I was saying about replacing D by D plus a gauge potential. Okay? So that is the general framework.
What happens in the commutative case?
You get nothing. They disappear. Why? There is something which is I didn't want to mention. It's a small nuance. It doesn't really complicate things, but it would make things heavier. You see, there is an identity, it turns out, between three different notions. I didn't write a transparency for them. It is important, though, that I mention this. Okay, it turns out that there are three things which are identical in this theory. You see, but this is really okay. So the first one is that, in fact, in the work, for instance, of manifolds, like the work of Singer, son of Sullivan, and all that, on characterizing manifolds, which is very important for what we want to do. We want to know that we are handling not every space, but spaces which are manifolds. So what is manifold? As I said, either you can define it by local charts and so on, or you can go much finer. And much finer means that the quality of manifold are the Pointryagin classes. But not arbitrarily. What the real quality is Pointryagin duality. Poincaré duality. And Poincaré duality, now there are several versions. And all of what I was saying was in K theory. Okay? But the true characterization of manifolds is not in K theory, it's in KO theory. Now what is the nuance between K and KO? It's not a big deal, it's a real structure. Okay, so in other words, the Hilbert space that we are dealing with, it will have a real structure. So it's a decoration on the spectral triple, okay, which is called a real structure. It's a J. Okay, now for physicists, you know that forever. What is this J? When you have spinors, you have charge conjugation. Okay, so it does coincide for physicists with what they call charge conjugation. Okay, so far so good. I mean, so far there's nothing much I said, except for one thing, which is absolutely great, which is that in non-commutative geometry, it turns out that this J coincides with the Tomita's operator, J. And what is Tomita's operator, J? It is something that tells you that there is some commutativity around in a non-commutative thing. And what is this commutativity which is around? It is that when you have an algebra which is represented in Hilbert space under good conditions, I mean, I don't want to detail the conditions, the algebra commutes with a big thing. And that big thing is J inverse for some real operator, which is Tomita's operator. Okay. Now it turns out that these three different structures actually are the same. Okay, in the general framework. And that's the definition of non-commutative manifold. Okay? Now I want to give you a non-trivial example because okay, I mean we know. Yeah. Space. Exactly. You see, a non-commutative manifold is something which is finer. Okay? Yes. Yeah, but it's weaker. The true character, if you want really to have a manifold, it's not enough to have Poincaré duality in complex case theory. You have to have Poincaré duality in the KO theory. Okay? Now, let me give you a non-trivial example. Okay, so, I mean, I don't want to give you the non-commutative torus because you know too well.
You don't want to give us what?
The non-commutative torus. Okay, I want to give you.
Non-commutative D in the space of dimension D that I could use for.
Well, okay. I prefer to give you something even simpler, to me far more important, which is the following. So I will describe a finite dimensional space, AF, HF, DF, which I will now describe. Okay. And what is this space? The algebra AF will be just complex numbers plus quaternions plus 3 by 3 matrices. Okay, I will explain a little more about this. This Hilbert space will just be the Hilbert space labeled by elementary up, left quark, down, left, up, right, down, right, with 3 colors. So it has certain dimension. Okay, and similarly for the leptons. Okay, fine. Yeah. So I'm going to say the following. I have a Hilbert space, of course. I have the standard model fermions. I have an algebra. I give you the algebra. Okay, and I have an operator D. What is it? It is a Yukawa coupling matrix. What I am saying is the following. I am saying that. So, and I take particles and anti-particles. Okay. So what I am saying is that it's an exercise to check. I didn't write the axioms of manifolds, but it's an exercise to check that the standard model fermions fulfill all the conditions. And in particular, there is this commutation, of D commutator A has to commute with GBG or something like that. This has to be true. And this condition is actually non-trivial, and it's there exactly because color is unbroken by the Yukawa coupling matrix. So what I am saying is the following. Now, the theorem... Wait. Well, I am defining a geometry. Okay, a geometry is given by a spectral triple. So it's given by an algebra, a Hilbert space, and an operator D. Okay? So I'm giving you the algebra, I'm giving you the Hilbert space, and I'm giving you the operator. Okay?
Are we supposed to find the gauge bosons of 321 from your construction?
Sure, exactly. Plus the X. The X will come out automatically.
I guess I see that vaguely with the choice of algebra.
Yeah, well, with the choice of algebra use.
Said how the algebra is represented.
No, I didn't say how the algebra is represented. Okay. Yeah, but it is very strange that it can be done if you want, because the quaternions have only one representation. Quaternions are not like SU2. You see, SU2 you can have any spin of representation. Quaternions, they have only spin 1/2. Because it's an algebra. An algebra has to act linearly. Okay? So what I am saying now, is this is an example. This is an example of a non-commutative space. Okay? It's just an example. All right? What is the Dirac operator? It is the Yukawa coupling matrix. Well, no. That's a zero-dimensional space. That's a discrete space. That's a discrete zero-dimensional space.
What's minus 1 to the F?
What is, sorry?
What's minus 1 to the F? Don't you need something that can't be?
Sure. That's left or right property of particles. That anti-commutes. Sure. Oh, everything is fine. Don't worry. Okay.
How do you get a spiral? I mean, why is the gauge represented
Well, okay. I mean, you write down the action.
Well, I mean, from this choice of algebra, I can start to see that there's a U1.
Yeah, sure. No, but I didn't tell you how the algebra is acting. Okay. You see, what distinguishes fermions, what distinguishes quarks and leptons is the action of this and this. You make a choice, of course. Yeah, sure. Okay. But I will come back to that. Okay. Now, the claim is the following. What is the theorem? First theorem is that if you compute the inner fluctuations of the metric for that, okay, you can do the computation. No, now you tensor, of course, with R4. I mean, you do exactly the same operation as for DIMREG. You tensor by R4. Okay? You tensor by R4. You do exactly the same operation as for DIMREG, but you tensor by this stupid little thing. Okay? And now you do the computation of the gauge bosons of that, namely the inner fluctuations of the metric. The claim is the following: the claim is that you get not only the gauge bosons that you expect, namely the gamma, the WZ, and the gluons, but you also get the X field. Yes, it is a connection. Let me explain you why it is a connection, and it's completely obvious. Let's take the simplest example of a space which is product of continuum by discrete. What is it? It is two copies of this space, the part which is on the top of the leaf and the part which is below. Okay? Now, on this space, I said this non-commutative geometry treats the discrete and continuum on the same footing. So if I have a function on this space, I can differentiate it on the top part. This has spin 1, obviously. Okay? I can differentiate it on the lower part. This has spin 1 too. But I can also take the final difference across. And that's the X field. And that has spin 0, obviously. Okay? It has spin 0 because it doesn't see which direction. You don't need a direction. You just need to go across. Okay? So that's the X field. And it's exactly how it appears. Okay? And it appears with the right couplings and so on and so forth. Okay? Okay. But now we are not happy. We are not happy because it's fine. We have, if you want, an interpretation of the gauge bosons as a piece of the metric, as a part of the metric, as the inner part of the metric.
You need representation for this six that you get.
Yeah, and you get the right one. Well, you get the right quantum numbers for the X field, which was not completely obvious to start with. No, I didn't put in the X field. No. You can tell me that I put in the gauge bosons. Yes, this I would believe. The gauge boson, yes, but not the X field. Yes.
Say that you get the X field, you get a count coupling.
Yes.
You get a kinetic term.
I am coming to that. I didn't tell you what is the action. How can you ask about a kinetic term if you don't have an action? Okay? I didn't tell you what is the action. I just told you that now the metric incorporates in its data the gauge bosons. That's all I told you. Nothing more. You see, what I told you now is that the metric has two pieces. It has a piece which is external, which is the G minus, ordinary G minus, and it has a piece which are the gauge bosons. But I didn't give you the action. Okay, so now let me come to the action principle. Okay, so what is the action? You see, what could possibly be the action? So we need, in order to find the action, we need an action principle. Okay, we need an action. Now, what I am saying is the following. Is that this action principle should be a generalization of the equivalence principle, in the sense that the action should be as invariant as it can be. Okay? So, well, usually not enough, but it should be as invariant as it can be. And in particular, it should have the same invariance properties as the observables, which are spectral. Okay? So the action, which we wrote down, is purely spectral, and what is it? I mean, I don't think there is anything simpler than that. The action is just the number of eigenvalues of the line element which are bigger than a given length. Or if you want equivalently, it is the number of eigenvalues of the Dirac operator which are less than lambda. Okay? When you take that function, you get a step function. Okay? Of course, I mean, you get a function which goes by steps like this. Okay? But there is a general mathematical procedure to replace it by a smooth function that goes across, plus an oscillatory piece. And the smooth function can be computed. And it can be computed actually by residues. It's a sum of residues. It's a sum of powers of lambda. Lambda is the cutoff. Okay? And residues. So it can be computed. I mean, that's a general fact, okay, which one can prove. I mean, it's pretty much, if you want, what happens in the heat equation and, in the zeta function. So you can compute it. Or ds is the inverse of d. I mean, ds is 1 over d. It's a line element. Yes. Capital S is the smooth part of the action. This is the spectral action, cut off at lambda. Okay? That's the definition. Yeah. Okay. So this is the definition. Okay. Now the claim is the following. The claim is the following: is that if we take the yes. Sorry. What is?
The sum is over K with only the 1 second.
Oh, this is a dimension spectrum. This is a dimension spectrum. Okay, I defined that before. This is a dimension spectrum. Yeah. No. It can be a complex number. This is a dimension spectrum. Okay. So that's the action. Okay. Possible dimensions which occur. where the residue makes sense. Okay, so there is this power of lambda, there is this 1 over k. Okay, okay. So now what is the claim? The claim is the following. Now you see, you take this stupid space I was explaining here. Okay, and you take the product. You take this space and you take the product with R4 Euclidean. Okay, and you go and you compute. The whole computation is local, and here is what you get. Here is the action that you get. Okay, so here is the action that you get. So this action has the Einstein term with a scalar curvature here, with a coefficient lambda square as it should. Okay. It has a cosmological term somewhere here, E0. It has this B0 turns out to be 0 actually. Okay, so okay, it is coefficient. All these coefficients have numerical values which come from the Yukawa matrix couplings and so on. Okay, so yeah, sure. As you vary the Yukawa couplings. Okay, so you get 1/4 the coefficient of the R square term. Well, it's a computation. Okay, okay. So this coefficient are not. Yeah, sure. Okay. So now what happens is that you get the Yang-Mills self-coupling of the Yang-Mills fields. So you get these 3 self-coupling of the Yang-Mills field, which are the ordinary ones. You get the minimal coupling of the Higgs field with the Yang-Mills field square. You get the quartic self-interaction of the Higgs field here, the quartic term of the Higgs field with the right sign. Very interesting question. I am doing the calculation of the spectral action for this non-commutative space.
Do you get any relations between the couplings?
Yes, you get the same relations between the couplings as ground unified SU5. Okay, for the Weinberg angle, which is not perfect, but which is not that bad, because we are not sure about the exact fermionic content. If you change the fermionic content, you will get the same prediction without ground unification as the corresponding ground unified theory. Okay, that's what you get. Okay, you also get the mass of the Higgs because you have the self-quartic coupling of the Higgs. Okay, and if you run it down, you get 160 GeV, something like that. Okay? If you run it down to our energies, you get something like 160 GeV for prediction for the Higgs mass. Okay, but of course, what? No, I mean this is essentially all that you get. I mean, okay, I mean, okay, let me sort of keep going a little bit. Now, what I would like to say, of course, I am not saying that this is any final theory or anything like that. I mean, this is just a shot in the dark, in the sense that it gives you an action which is not that bad, and which has the following properties. This action, because it's counting a number of eigenvalues, is obviously positive. We are working in Euclidean. So it's very natural to take it as exponential minus the action when you do a Euclidean functional integral. Okay? Well, yeah, but you see, the point is that because it's a number, I smeared it. Okay? As I said, I smeared it. But this action was just counting a number. It was just counting a number of eigenvalues. So a number is a positive number. Okay? Now, so if you want when one tries to go further, okay, so I just explained this. Well, no, I'm not talking about that. Okay, so wait a second. So now I don't want to. So okay, I didn't say how the Higgs and so on occur for standard model, how the hypercharges occur and so on. I didn't talk about this. Okay, but yeah, C is the Bayes tensor. You get a C squared. What? A0 is possibly non-zero. It's non-zero, no. Okay. Oh, okay. E0, very good. E0 is a fundamental question. The point is the following. Okay, and let me make a big shot in the dark now. Okay, so let me write a functional integral which is totally wrong, I'm sure, but it's just a shot in the dark. Okay, for gravity. Okay, so the functional integral is the following. I take this spectral action and I take a spectral observable. Namely, I am saying I am trying to do gravity in the Euclidean functional integral. So I take an observable which is spectral. So it only depends on D and say some fermion in an equivalent way. Okay, and I write something. Okay, so I wrote. I think I saw somewhere a paper by David Gross in which there was also D of D. Okay, so what I claim is that now I have a matrix model because the Dirac operator now is an Hermitian operator. Okay, and I claim that the spectral action is in fact begging for making a cutoff of the Hilbert space of fermions to all fermions which have energy less than lambda. So it's begging for doing something in a finite dimensional Hilbert space. Okay? And now I come to the E0, to the cosmological constant. What you have now, there is a big problem. The big problem is that not all Hermitian matrices qualify as the Dirac operator. Of course not. Okay? So what one has to write down are the constraints, which I sort of skipped very briefly before, on a Hermitian matrix that it qualifies for a Dirac operator. Now I said that this is an equation in general whose degree is the dimension of the manifold that you are talking about, of the space you are talking about. Okay? And what is this equation? Why is there an equation that relates the Dirac operator, okay, with the coordinates? Why? Well, you know, when we made the calculation of the gradient, you know, when we want to compute the distance, remember that when we compute the commutator of a function with the Dirac operator, we got the gamma of the gradient. But if you give me enough linearly independent gradients, I can get gamma 5 at every point. Okay? So you can imagine very easily that you can write down a linear combination of functions that will produce gamma 5. Okay? Now, and this is arbitrary dimension. Now I claim that this equation is exactly the roof that holds things together, because it's telling you really that you have local coordinates. In other words, around the point, when you will extract enough coordinates to get the gamma 5, you realize that the Jacobian doesn't vanish, exactly because of this condition. Exactly, okay? So now, if you want, when you look at this constraint, what you find is that you are not doing gravity, you are doing unimodular gravity. In other words, you are doing gravity in which the volume form is prescribed. Why? Because when you write this condition, you will find out that the volume form of your Riemannian metric is entirely prescribed. Yeah, you have given up scale transformations. Okay? So what happens? No. It is gamma. It's very important to require that and to do this like this. Okay? I mean, in odd dimensions, it would be equal to 1. This equation can be rewritten for the circle. U star du is 1. It is the same equation as this one. Okay? So what I am saying is the following: is that when you do this theory, you don't get the Feynman integral over all geometries. You only get the Feynman integral of geometries which have a fixed volume form. And when you do that, you know very well that the cosmological constant disappears, because it appears in numerator and denominator, and it cancels off. Okay? So if you want, much of the work that I did over the last 3 years is motivated by this. I put a recent paper on the ePrint archive with Michel Dubois-Violet, in which the motivation was we studied this constraint, and we found that this constraint, in fact, had non-commutative solutions, which are the non-commutative spheres. And then, you know, we spent enormous amount of work to study these non-commutative solutions. But the idea is that the idea of this general theory, if you want, is that, okay, there should be a way to write down a matrix model. It will be a matrix model because of what I said, because the Dirac operator is a Hermitian matrix. And the fact that one works in dimension 4 will mean that the constraint, if you want, the sort of Lagrange multipliers that you will add, will not have degree more than 4, which is not a bad thing for, you know, trying to use general techniques, the matrix models, and so on. So I mean, the situation like this, if you want, is that one has this proposal, and okay, I'm sure it's wrong. You know, I'm completely sure it's wrong, and so on. But what I'm saying is that at least, if you want, it gives the hope that one can at least compare. Because here there is a spectral action, it's something which is well defined, which you can compare for different space, and so on and so forth. And the hope is that by varying the space, by looking at all possible solutions, commutative or not, and so on, okay, at least one is completely sure that one is not far from real physics. For the reason, if you want, that, okay, the standard model is this very, very simple example. And for the standard model, you know, I forgot to say one thing, which is that the main criticism you could have for the standard model is, after all, why on earth did you choose this one? Okay. Now, I don't have... Yes? Yeah? No, let me finish on this, okay? So if you want the standard model, it's true that I put in by hand this space. Okay? And, okay, might be this space... Okay. Now, what is the explanation, if you want? What is the philosophy that I have behind this? The philosophy is the following. You see, It's very strange what happens in physics, because we start with Maxwell-Dirac Lagrangian, and we say it is the Maxwell theory that prescribes the geometry of space-time, and this is Minkowski space. And then, whenever we find a new interaction, like the weak interaction and the strong interaction, we put in new particles into space. But this is bizarre, because after all, we should start from the full Lagrangian of all the interactions we know, and we should derive space-time from there. What I am saying is that this is exactly what non-commutative geometry does. It tells you that there is a small nuance between what you would get if you had Maxwell-Dirac and what you actually get if you take the standard model Lagrangian. And this nuance is very minor. It's a very minor amount of non-commutativity, which is coming from this finite discrete space. Okay? Now you can ask, fine, that's a sort of experimental effective theory where you see some details of space-time at a certain scale. But what could it reveal? Okay, what could it reveal? And it turns out that there is an idea which is not totally off, I think, which is not yet done, okay, which is, so it's, if you want, it's an open problem, but which is not so far off, I think. And this idea is the following. This idea is that when you look at what happens for the standard model, namely when you look at this algebra, I remember when I talked to Atiyah about this algebra, and Atiyah was repeating, it's not nice to have only one quaternion. You should have one quaternion left and one quaternion right. Okay? Now what happens is that because the neutrino has a right-handed component, okay, one can actually make a better algebra than this one. But it would require that one works out the theory where you have a weak isospin right. And I don't know how far one can go with that, if it is. But it is what you have in a certain. Well, let me just finish. Okay. So what I want to say is the following. What I want to say is that what could happen, but I am not sure, and absolutely not sure, is the following: is that in fact the content of particles of the standard model is simply spinors. But it's not spinors with respect to the ordinary Poincare group. It's spinors with a slight extension of the Poincare group, which is an extension at cubic root of unity. And you can ask me, where do you have cubic roots of unity? Well, then it's that you don't know the hypercharges of quarks, which are fractional with the denominator 3. Okay? So it turns out that when you work out the extension in Euclidean we have spin 4, which is equal to SU2 cross SU2. And it is well known in non-commutative geometry, if you want, that there are extensions of SU2. Namely, SU2 is a simply connected group. In the commutative world, SU2 is the end of the story, not in the non-commutative world. In other words, in the non-commutative world, there are coverings of SU2, like at cubic root of unity, which have a finite kernel, which is a finite group, quantum group, okay, which cover it. Now, it is quite remarkable that when you look at the spin representation for this extension, you find something which looks very, very similar to the representation I was writing. Okay, so I mean, this is not done. But you know, it would give some extremely satisfactory geometric understanding of what we find. At the moment, I put it behind. I mean, you know, yes.
I have a bunch of
Yeah.
questions. Well, first of all, just
Yeah.
why do you understand the point of what
Yes.
you did? You have not much input, therefore.
Yeah.
Mass scale you get out should be the same as stuff that you include.
Sure.
I don't see how you think that differently like that.
Oh no, I take it as something at a certain very high energy, and then I run it down.
So it starts out as the Planck mass.
Sure,
You run
and I run it down.
Planck mass
Sure.
by 19 orders of magnitude,
Yeah.
you say you have a prediction.
Yeah. Well, if you have the big desert in between, of course. I mean, you know, I am assuming there is. It's not grand unification.
You can't make any prediction.
Yes.
Okay, so what you really have there is the
No. Let me tell you why. No. The answer is very simple. You know very well that if you take the standard model and you try to run it very high, the quartic coupling of the Higgs will blow up. Okay. So it's exactly the same type of constraint.
you put,
Yeah.
therefore,
Sure.
cancel everything.
Of course.
And Planck squared, minus a Planck squared. But I don't think you get a prediction.
No. I mean, there is a prediction for the standard model which you get very easily by saying that it doesn't blow up at a certain energy scale. And this is the same thing as it is.
Anyway,
It does.
The other question I have is
Why not? I mean, it's exactly the same thing. It's exactly the same thing. Here I am saying that there is something at a certain energy level, and you can. Right. Sure, it's a bound. It's a bound. Yeah, sure, it's a bound. Yeah, sure. No, I mean, I'm not saying 160 on the nose. I'm saying it's a vague order of magnitude which you get, and which is not off target, if you want. I mean, it's a consistency requirement. It's not a prediction. No, of course, it's not a prediction. It's a bound. Yeah, sure, it's a bound. That's perfectly right. Yeah, sure.
Now,
It's a stability bound. Yeah, I don't know.
right. Now, the
Yes.
other thing is
Yes.
why you're saying you can't consider.
Yes.
I would have liked to have seen.
Yes.
A non-perturbative definition of dim ray.
Oh no, but okay,
Yes.
fine.
Without.
Yes.
Because for me,
Yeah, you are right. No, the fact that there is gravity, I agree. I completely agree. I completely agree with that. I mean, the fact that one picks up the gravity term as well, okay, which is a dimension-full term, is not nice. I mean, because we know that dimension-full terms are a pain. Okay, I mean, we know that, of course. And in similar way, you know, what is funny is that the gravity term, the scalar curvature term, occurs on the same footing as the h² term, the quadratic term for the Higgs.
you don't know how to write down.
And I don't know, I mean, except you could artificially eliminate these terms by saying they are dimension full and I eliminate them. But this is not nice.
There's nothing that just measures
Yes.
the curvature of the Higgs.
What do you mean? Oh, no, of course you have. No, but you have the terms which measures.
Everything else together, the gravity.
No, but if you look there at terms which are homogeneous of degree 0 in lambda, you get exactly the standard model. Sure.
Well, except for the R squared result.
No, the R square term is not there. It's coefficient 0. The C square term is there. Yes. Sure, but in flat space there is no C square term. I mean, if you want to look at the standard model in flat space. Sure. It's there anyway if you try to move gravity by normalization. Sure. Yeah. Okay. No. I understand your question. Then let me answer. You see, the point is that ordinary renormalization you can do on the leaves of the internal fluctuations of the metric. And then the scalar curvature that is fixed. It's only the gauge bosons that move.
So why can't I find an action that is calculated?
It is this action. It will be you will add a constant which is a scalar curvature, but it will be a constant. So it is there, of course. It is there. You see, no, let me tell you. It is purely geometric, okay? So it's an action on matrix. It's an action on matrix.
As you vary the rock operator.
Yes?
Look at that functional interval.
Sure. Yeah, no, okay. Let me put in the spectral action. So when you look at the spectral action, you put the spectral action, what you find out is that there are terms which depend on the curvature, depend on the metric and so on, and there are terms which don't. And the terms which don't, you have exactly the right ones.
But when I'm doing that,
Yes.
I'm doing that interval of D.
Yeah.
If I vary D, I'm also varying metric.
Yeah, but you can vary the metric only by, if you want, only on the leaves. Sure. And then you are fine. Then you are doing field
I
theory.
wouldn't write it as an interval over D.
No, then you would write integral over the inner fluctuations, of course. By the way.
Is there a way of doing that for?
Sure. Yeah. Sure. No. Let me make several points. You know, there is a very important point which is related to what you say, because when we do the functional integral, we are secretly using the linear space structure. We are not saying it, but we are using it. So when you write, for instance, the integral over the gauge bosons, you are using the linear space structure of the gauge bosons. Okay, the A. Well, the fact that it's an affine space. Okay. Now the beauty is that they are added linearly to D. So it's very encouraging for doing a functional integral where you take D of D as a matrix, because D is moving linearly by the gauge boson. That's what I mean. You see? Okay. But now, indeed, it's correct what you say. You can restrict this functional integral to only the inner part. Okay? Fine, you can do that. You can certainly do that.
Well, that's
Yeah, sure, of course. No, I completely agree with that.
if I do
yes, yeah,
then,
yes.
Then the relevant parts of the action.
Right, is correct. You get exactly. Sure. Exactly, and you get the right one. Sure, that I really can prove.
So,
It's even a general theorem.
so you can take this action
Yes.
which sort of measures the
Sure.
number of items
Right.
you
Sure. And restrict it to that, of course.
restricted to
Sure.
variations.
Sure.
If I could vary
Sure.
that action with respect to
Exactly.
these inner ordinals.
Sure, and then you get that. You get the correct thing.
Some kind of
Yeah.
analog,
Sure.
maximum.
sure. Exactly, sure. Plus the x. You have also the x there. Yeah, you have the x. You don't want the x, well. Well, okay, to get pure gauge theory, it's very simple. Instead of taking the space, which is that space, you take the algebra to be n by n matrices over C. Okay? And then the group that you get is SUN. Right, and the spectrum of that algebra is 1 point. Then you get SUN and you get Young-Mills. Fine, times are 4, of course, times are 4. Fine, okay, then you cross again by the space of dimension Z. You cross by the space of dimension Z. Yes?
Will that give me, the question is, will that give me...
Well, I know that, well, okay, no, it's a very good question, sure. But the answer is, for the moment, we have only checked, fine. The answer is, for the moment, we have only checked, because we wanted to look at anomalies, the diagrams which have only fermionic internal legs. We didn't look at the bosonic diagrams. Okay, so I cannot answer your question because there is still some check to be done. We didn't care about the others because we wanted the anomalies. Okay, so but it's a computation which can be done. Okay, I mean, and one should do it, of course. But the answer is, for the moment, okay, we only check this. Yes. So tell me what bothers you, because yeah.
First, I guess I don't know how to do it.
Well, the calculation in any case, it's
yeah. But
yes.
If you just take this algebra,
yes,
operator,
yes,
and
yeah.
times are 4.
In that case, times are 4.
Discrete side.
Yeah, it's just nothing. It's nothing. It's a few points. You know, it's like these two. It's 3 points. It's nothing. I mean, it's nothing. It's. And on that, but then you have to carry out the work.
But there too,
Sorry?
well, which space is it?
Well, no, I didn't tell you what is the space of dimension. So, the space of dimension Z is a very important topic. So, the space of dimension Z, I mean, what happens, the real point about the space of dimension Z is what happens when you compute the X of the spectra of the operator. So it has some operator d sub z, if you want, and you raise it to this, okay? And that has to be given by a formula. Might be I'm wrong, but it's like pi lambda to the power z, perhaps over 2. I mean, if you want, it has to be to obey a very specific equation, which you can find a solution for this equation, okay? And you can describe the space entirely. You have an algebra also.
Which becomes the algebra function on R4 as we get
No. This is a zero-dimensional space. You cross it by R4. You see?
I think David's trying to cross this.
No, but you see, you have 3 space that you have to cross. You take R4. You take R4. Okay, times the space of dimension Z. Okay? Times the small space of the standard model. I mean,
So if I just want to do a scalar,
you don't even bother about this. Okay. I mean, you can do a gauge theory with UN, something like that. Okay? So that's the idea. Now, this space requires a lot of study. With Mathilde, we have a model. Okay, we have a very good model for this, but it really, I mean, we don't want to say too much about it. But
so this is not yet really done.
It's not written. What is done is that we can prove that for all fermionic graphs, when we do computation with this space, we get exactly this Brayton-Ollner-Mason prescription. Well, yeah, sure. With the direct product, we get the exact prescription, we get the vanishing gauge potentials, we get the correct integrals for the fermionic diagrams. This is what we can prove. Okay. To go further, okay, when we'll have to do much more work, of course. But if you want, now let me finish with my mental picture about space-time. Okay. Okay, so what is my mental picture of space-time? So the mental picture I have of space-time is the following. Is that we have indeed the continuum, and we have this space of dimension Z, and we have this F. But when we go to Z equals 0, we don't do it in a stupid way. We use the universal singular frame. I mean, we use this very, very, very special frame, which instead of going stupidly to dimension Z equals 0, goes according to this very strange This connection, exactly, with these counter terms. Okay, so that's the idea I have. And what I would love to do is to get a better, more convincing geometric model of that would actually renormalize geometry in the correct dimension. That would be the idea. Okay, so that's a dream, if you want. That's a vague mental picture that I have. Okay, but my belief is that one cannot even begin with trying to quantize gravity and all that before one has completely absorbed the lesson from quantum field theory, which is that indeed the picture that we have of geometry in dimension 4 is not right. It's too naive.
Well,
Okay, that's a belief that I have.
there is another point of view that
Yes.
excluding gravity, that
Yes.
relations that there are other regularizations.
Yeah, but you see, I agree with that. But I spent part of my life working with local algebras in algebraic quantum field theory until one day I realized this had nothing to do with physics. So I much prefer to take something that physicists actually use in CERN to do computations, whatever it is, take it seriously, than whatever else. You understand my point? I mean,
Well, what do you think of the fact that
yes,
new quantum field theory,
yes.
by working in 4 dimensions with some other regularizations?
Well, okay. As I said, I trust this thing which is constantly checked by experiment. That I trust.
No, they all are equivalent.
Yeah, I know, but
You can work with them.
yeah, but for instance, I would hate to use analytic regularization, for instance, because it would complicate things tremendously.
Analytic regularization is bad. I would
It's
have
bad.
made the argument, if you want an argument,
Yes.
I would have made the argument, I was just
Yes.
to see what you would say,
Yes.
that the other regularizations that
Yes.
are nice
Yes,
all screw up things in the ultraviolet.
they do. I
They
see.
all introduce artifacts.
That screw up the symmetries. Yeah, sure, if you
They
want.
don't
Yeah,
necessarily screw up the symmetry.
I see.
You know?
Okay,
But
okay.
they always modify.
Yes,
so
yes,
that
yes.
They keep space the
Yes,
same.
right.
They modify things as they.
I see. Okay,
Whereas
okay.
here,
Yes,
dimensional regularization,
yes.
maybe one isn't doing that if one knew what the hell it meant to talk about before.
No, but now we know. What I mean is that, at least now we begin to have a mental picture. No, but the point is the following. You see, one of the, non-commutative geometry is at the moment, it's a building site. It's not something, okay. So one has to experiment and wants to be open to criticism and all that. And I am the first skeptic. I mean, I am the person which is most skeptic. But when I realized that there was this space of dimension Z that actually were fulfilling the right property and so on for these diagrams, then I began to wonder. I began to wonder what is going on, And really, I mean, the point here is that I'm pretty sure that the answer is infinitely more complicated than what I am saying here, in the sense that this Galois group of the motivic Galois theory and all that, will also be present. And how will it be present, How will it be present? It will be present because of one thing, the final thing that I want to say, which is that, I don't think physics is done over complex numbers. Because when you physicists talk about constants, they are not constants. They depend on the energy level. They are running constants. And one of the great properties of non-commutative geometry is exactly this, that you can dress the geometry. You see, the geometry is given by the propagator. The line element is given by the propagator of fermions. Now the propagator gets dressed by inputting all the quantum corrections. That means that the line element gets pressed. And that means that the geometry is running. So this means that this formalism of geometry is able to incorporate the quantum corrections in the geometry.
Well, it's scale. I mean, it's really only scale.
Well, the scale dependence of the geometry. And one belief that we have with Mathilde is the following, is that this symmetric group that we have found, this cosmic Galois group actually, is actually a Galois group on the field which extend the complex numbers with which you have to do physics. You shouldn't do physics with scalars, you should do physics with scale-dependent numbers. Okay, and I mean, except if you believe that there is a fixed point for the renormalization group and that everything is asymptotically free. Okay, but I mean, I sort of have doubts about this. So I mean, the idea is the following: is that instead of trying to find a unique theory and so on, no, everything will be scale-dependent, and everything will be working over that field. And then, okay, potentially, if you want, this Galois group will act on that field. I mean, but this is very vague. Okay, again, okay. I mean, these things are so difficult that. Yes.
This space is
Yeah.
adequate for gauge theory.
Yeah.
This one we just built up.
Yeah. Sure.
one of the simplest. You have an
Yeah.
action, which is
Sure. Spectral action, yeah, sure.
this is spectral action.
Sure.
Restricted.
Sure. Restricted to the gauge potential. So the inner fluctuations, yes. Right. Yeah.
What is the what are the extreme of that? I mean, is that a problem that
Aha.
defined?
No. It's very well defined and all that. You see, no. I mean, let me tell you the story because there is a very beautiful story there. So the story is the following. The story is that you could take this action in any dimension, in a space of dimension, whatever you want. Okay. What you can do the computation, and what you find is that part of the action, the inner fluctuations, okay, it doesn't exist in up to dimension 3. In dimension 3, it's purely a Chern-Simons term. So it's not, it's coming from a cyclic cocycle. And it only begins to exist in dimension 4, where it's given by Young-Mills. So it does not exist at all until dimension 4, where it's Young-Mills.
I'm not sure what that means, but I thought about until.
Well, what I mean is that, no, but it's on the D, if you want. What I am saying is that, you have the D and you have these inner fluctuations, all right? And I gave a class in the Collège de France several years ago in which I explained that. You have to assume that the geometry has no tadpole. What does it mean that the geometry has no tadpole? It means that when you look at the inner fluctuation of your operator D, there will be no linear term in A. If there is a linear term in A, you can go to a place where there is no linear term in A. Okay? It's true for Riemannian geometry that there is no linear term in A. I mean, it's true that if I take Riemannian geometry and I tensor it by n matrices, it is at a local minimum. It has no tadpole. Okay? So once you have no tadpole, then you can begin to do calculations. You find that there is no term until you are in dimension 3. In dimension 3, you find that there is a 3 cyclic cocycle that gives you the Chern-Simons actions, completely generally. But of course, it cannot be at a minimum because it's not it's topological. And then you find that the first dimension in which it can exist with a minimum is 4. It's dimension 4. So a vague idea that I had was that one should do a functional integral over all these things, and they won't see anything up to dimension 4. Essentially, they will only begin to feel something in dimension 4. And beyond dimension 4, there should be a problem because of this constraint on the D that will be of higher degree than 4. I mean, it's a very, very vague thing, but I have the feeling, that what we need is a very good extension of geometric notions, very flexible, okay? And that then we need to re-understand renormalization in these terms and reformulate everything geometrically. I mean, that's the main idea, if you want, okay? Now, it can be that non-commutative geometry is not yet there and so on. I don't know. But this is the idea. The idea is that we have to extend our concepts of geometry, the G-news and all that, in a way that will absorb all these things, and will be flexible enough and so on. So it's a step in that direction. Okay.
Done?
Yeah.